Good afternoon. It is my great pleasure to give this talk to you today and share with you my perspective on the topic of how technology advances in self-powered wearable sensors can enable pervasive health and environmental monitoring. The Centers for Disease Control in the US has already reported that chronic diseases such as heart disease, diabetes, and lung diseases are the leading cause of death and disability and consume the majority of the nation's healthcare costs. If you look at the annual global data, the story is the same in that it also shows that chronic diseases are the leading causes of mortality. As if this was not enough, the recent COVID-19 pandemic has dealt another big blow in that it has shown a clear correlation with chronic diseases. The high hospitalization rates and sadly the mortality rate associated with COVID and conditions like hypertension, obesity, and diabetes is alarming and warrants the need for prevention of these lifestyle diseases. Therefore, the management of chronic diseases is essential, but currently it's not effective and hence it's costly. Let me walk you through the main reasons why current management of chronic diseases is not effective. At the present time, the current medical plan involves a single treatment that fits everybody, but it does not. For example, not everybody's blood pressure is abnormal just because it doesn't fit in the average range, and not everyone will respond to weight loss plans if they are given the exact same diet. What we need is personalized diagnostics that can provide a much better outcome for the individual and also be a tremendous resource for our healthcare system. So how do we get there? Well, currently we have individuals whose health status is assessed very sparsely throughout the year, and a complete picture cannot be built. The way to overcome this is by enabling individuals to monitor their health signals over long periods of time. Why? Because studies after studies have shown that longitudinal data enables better understanding, detection, management, and even prediction of diseases. Not only can this data be used to improve an individual's care, it can be combined with data from other individuals to enable more precise population health management. By having more and more people get long-term data, more precise population health can be achieved by getting more granularity and creating subgroups within population. So what can we do in the engineering research community to help in this direction? We can enable continuous regular monitoring for individuals that can provide actionable and empowering data. Hence, what we are looking for is long-term monitoring and management of multiple chronic disease health targets that can lead to a paradigm change in health outcomes. And while there are numerous and popular wearables on the market, most of these do not have the features to achieve the paradigm that I just discussed. And also, in many cases, they're too costly for everyone to afford. So what we need are self-powered and multimodal wearable devices that are cost-effective and can enable a much more sophisticated picture of health. This is precisely the goal of the center that I lead. In the ASSIST Center, which stands for Advanced Self-Powered Systems of Integrated Sensors and Technologies, and funded by the National Science Foundation in the US, we are building technologies that are always on. And we are achieving this goal by ensuring that the power that's generated is renewable and it's from the human body itself, so it's always available. And the power that's consumed in the sensors and electronics is as low as possible. At the same time, we are also ensuring that these devices are wearable and the data that's coming out of these devices is actionable. This center is a partnership of 8 universities shown down here, along with an industry ecosystem where we work together with industry to advance many of our technologies. So the vision of the ASSIST Center is to create self-powered sensing, computing, and communication systems to enable data-driven insights for a smart and healthy world. The characteristics and the unique traits of our devices are that they're self-powered. They have multiple sensors, including physiological, biochemical, and environmental sensors. They're wearable, wireless, and comfortable. And the data that's coming out of them is informative and continuous, leading to new understanding. By having such technologies that are always on and that have multiple sensors, we can enable continuous health monitoring for chronic disease management. And what can this enable at the end of the day? Well, we can look at data sources from different sensors and understand their correlation and create new digital understandings called digital biomarkers. We can also use this to explain, influence, and predict health outcomes and gain fundamental insight into disease origins. So here is a block diagram of our wearable devices. This is a pretty generic block diagram, but I'll show you where our center and our researchers are creating advances. This block diagram consists of a wearable node that has these the microprocessor where information is computed and computed and communicated. It also has sensors for different kinds of health and environmental monitoring. It has energy harvesting, energy storage. It has antennas, and it connects to a phone or an aggregator through wireless Bluetooth communication. In each category, we have several technology options that we are pursuing in the center, and these are being integrated together to build interesting systems. For example, in the area of energy harvesting, we are looking at body heat, body motion, but we're also looking at solar energy and ambient Wi-Fi, even magnetic and biochemical. In the area of sensors, for example, physiological sensors, we're looking at vital signs and also biochemical sensors. For environmental sensors, we're looking at different kinds of gases, such as ozone, and also volatile organic compounds, specifically specific volatile organic compounds and particle, PM monitoring, particulate matter monitoring. Instead of relying on only batteries, we're also looking at supercapacitors that have both high energy densities and power densities. We're also looking at antennas that can be placed on the body and still provide good performance with good efficiencies. And we are building state-of-the-art systems on chip that have ultra-low power radios and also ultra-low power system on chips and ultra-low power analog front ends. All of these technologies are being combined together into wearable systems that I'll discuss a little bit later on. And finally, as I mentioned a little bit earlier, we're also concerned with wearability and human factors because we want to ensure that any technology that we build must be adopted by the user. Once the data is transmitted to the aggregator, which could be the phone, it is analyzed either off the node or even on the node, depending on the use case, and sent for data analysis. So our cutting edge research that I showed you before is organized into these 4 blocks here. Energy harvesting and storage, low power sampling and sensing, low power circuits, and system integration and usability. Today, I'll give you a few examples of the use cases that we are addressing, and then also some examples of commercialization from our research team. So I'll begin my discussion with use cases and show you what research that we are performing enables these use cases. So the first use case is Vigilant atrial fibrillation monitoring. Atrial fibrillation is defined as irregular and often rapid heart rate that can increase your risk of stroke, heart failure, and other heart-related complications. And these episodes can come and go. Detection will require continuous monitoring of the R2R signals, the timing between R2R signals, and even when somebody is diagnosed, they will still need post-diagnosis monitoring to understand the frequency of episodes coming back. So to enable such a use case, what we need in the monitoring device are a few key features. First is we need vigilance. We need to make sure that these devices are self-powered and they're always able to monitor the ECG signals. The form factors are also important. They need to have dry electrodes and they should be comfortable so the user will keep them on continuously. The sensors that we have on here consist of course, the ECG sensors, electrocardiogram sensors, and also motion sensors. The measurements should be continuous. The sampling of ECG should be continuous. And to really detect real-time events, we need to make sure that the data is communicated in a low power scenario. So to enable vigilant cardiac monitoring, there are really 3 form factors that one could pursue. One is a self-powered or a shirt, a garment that has the electrodes inside the garment. Another one is on the arm, where electrodes can monitor ECG signal on the upper arm. And the third one is instead of a shirt, there's just a patch or a set of electrodes that are placed in the right positions. I will talk to you about the shirt first, and then show you some advances in the arm and the chest patch. So we have recently built a Vigilant ECG shirt that does not have a battery. It relies completely on the energy harvesting. It is end-to-end functional. It is wearable and self-powered. Here is Braden, one of the students in our center, who is wearing this Vigilant ECG shirt. You can see the signal is being transmitted. His ECG signal is being transmitted from the shirt to the phone. The data has some noise in it. This is raw data here that you're seeing. The shirt has thermoelectric devices right there, the antenna on the other side, and behind the shirt are all the electronics. As Braden will move, the signals are intact and keep getting communicated to the phone. Again, I want to remind everybody that the entire system is powered by thermoelectric devices, which I'll talk about in a second, and does not have a battery. The distances between the phone and Braden's location are quite large and can still receive the signal. So what enables such a shirt? There are a few key features. For example, this shirt has smart textile integration that has dry inkjet printed electrodes. It also has energy harvesters in the form of thermoelectric devices. It has an ultra low power system on chip, ultra low power radios. Also alongside, it has flexible antenna and high energy density supercaps that I will not touch today about because of time constraints, but wanted to mention that these components are all coming together in this shirt. So let me first talk about the thermoelectric generators. So here's a simplified view of a thermoelectric device that's placed on the body and harvests body heat. The device is a series of P-type and N-type legs connected electrically in series. The heat flows through the device from the skin outward into the ambient, providing a small temperature drop across each leg. Since the legs are connected in series, the small voltages can be added to generate a larger voltage. We are interested in flexible thermoelectric devices instead of rigid ones. First, flexible devices can be conformal on the body and provide more comfort. They can achieve a smaller contact resistance because parasitic losses are reduced. At the same time, having a single flexible device instead of multiple rigid devices has significant advantages over connecting small devices in series. It also leads to simple integration, more aesthetics, comfort, and all of these contribute to compliance. One of the key enabling technologies that we have in our thermoelectric devices is liquid metal. The liquid metal that we use here is eutectic gallium indium. It is a liquid at room temperature, and therefore it provides ultimate stretchability. It is also metallic with a resistivity of 2.94 microohm centimeter. The bottom line is that the contribution of the interconnects of the liquid metal to the total resistance is negligible. This is a characteristic and a feature that no other flexible interconnect can achieve. And this is important because the power is inversely proportional to the total resistance of the device. And let's look at how this device performs. So if you have a device that's about 40 centimeters square placed on the wrist, we measured the performance under 3 different scenarios: when the person is not walking and it's indoors, when a person is walking and it's indoors, and when a person is walking and it's outdoors and it's actually cold outdoors. In these scenarios, there's some interesting observations. Even when somebody is indoors and not walking, we are able to generate over 100 microwatts of power. As the person starts walking, there's air movement on top of the device, which leads to a higher temperature drop and produces a much higher power. But the interesting scenario is also when somebody's walking outdoors, where we can now get over 1 milliwatt of power. And as I'll show you in a few minutes, these power numbers are quite compatible with the power consumption of our electronics. And when we benchmark our devices to what's been published in literature, at the present time, we are beating all of the other reported values in terms of our power densities per area. Let me now move to the other side. So it's not enough just to work on harvesters. You also have to reduce the consumption of the system on chip and the radio. in this sense, we have a multi-chip solution based on subthreshold CMOS devices. And this multi-chip solution has many components. It has a low power chip-to-chip I/O. It has non-volatile memory. It has SRAM, analog to digital converters. It has AFE for ECG for the shirt. And it also has a radio transmitter. The transmit channel transmits only one advertising channel packet with open loop direct modulation after every frequency calibration cycle. The entire system operates at power of less than a microwatt, which is the reason why I mentioned earlier that our thermoelectric generators are operating at power levels that are much higher than what's needed. So this is a situation which is desirable. Our Bluetooth radios are compatible with Bluetooth phones, and these are operating at a significant power reduction. As an example, our radios are consuming 0.5 milliwatts of power, which is 8 times lower than a typical low power commercial Bluetooth radio, and 150 microwatts lower as well. Our antennas is another important piece of electronics. These are low profile, very thin, flexible antenna devices that have been designed to have efficiency of 83%, and they're stable under bending and body loading. Another critical area is user comfort and wearability. We have used a textiles garment as the wearable platform with screen printed electrodes that are immune to accelerated washing cycles without any loss in performance. As you can see here, after 3 accelerated cycles, there is still a very good signal to noise observed on the ECG measurements. We had designed the shirt for the best placement of each technology component. For example, the best placement for the electrodes, the best placement for antenna and the thermoelectric devices, and on the back side, the location for the electronics. A little more about the shirt and the electrodes. This is a whole garment knit design. ECG shirt was designed, fabricated using whole garment knitting for customized garment design and direct write printing for conductive pathways on the textiles. Translation of the ECG shirt to our ECG platforms is underway. This past year, we have also added the armband form factor for more ease of use for individuals wanting to have continuous ECG monitoring. However, this comes with the requirement of electrode placement that's a little bit more strict and noise removal to get the best ECG arm signal possible. This is because the ECG signal on the arm is lower in amplitude than on the chest. Textile optimization using compression fabrics is also critical here. We have undertaken all of these challenges and we're currently building devices that enable a self-powered ECG armband. We're also looking at multiple harvesting modalities, so not just a thermoelectric generator here, but also thermoelectric and a solar cell combined together to enable us to get the maximum power available under all scenarios. In addition to thermoelectric generators, we're also looking at other harvesting modalities. In this case, foot heel strikes can generate quite a bit of power. This direction of harvesting is not new, but our contribution to this field is in new materials and new designs. We're looking at new transducers that can enable almost 2.5 milliwatts of power harvesting at a walking speed of 3.5 miles an hour. And we are also looking at new materials like flexoelectrics that enable us to get lead-free harvesting of foot motion. The initial prototypes of this device are giving some good results, and we expect that this can be added on to our harvesting platforms. The second use case I'd like to talk about is that of asthma. In the case of asthma, there are about 300 million people that are affected worldwide. And this is data according to Veena. And out of that, 7 million in the US alone are affected, children are affected. And typically with children, the vulnerability to environmental toxins is much greater. It also is known that 50% of adults with asthma have uncontrolled asthma. So what is asthma? It's really characterized by airway inflammation and smooth muscle hyperreactivity. A normal airway looks open and wide, whereas asthmatic airway shows inflammation. The way the treatment is handled currently is you avoid the exposure to whatever is triggering the asthma response, and then you provide rapid medication that treats the airway inflammation. We are working with the UNC, University of North Carolina School of Medicine in terms of testing our asthma platforms. So what kind of devices do we need to be able to monitor asthma properly? Well, first, we need long operational lifetime because we want to be able to provide continuous monitoring. We also want these devices, especially if we're helping children, to be wearable and comfortable with open access to the environment. The sensors that we need in here should contain both environmental sensors like ozone and volatile organic compounds, but also health sensors like respiration and activity. We need correlation of the health and environmental data to understand the connection between an environmental gas and the response of respiration, and we need real-time communication. These specifications can be translated to the sampling power requirements, the range and sampling rates, depending on the use cases. So here is an example of our asthma platform. It consists of two locations, a chest patch for measuring ECG, microphone, heart rate, accelerometry, and even skin impedance, and a wrist platform that looks at environmental toxins like ozone, VOCs, pulse, heart rate, accelerometry, and temperature humidity. We have been able to mature this platform to quite a significant degree. We have multiple human subject studies that are currently going on. And in recent months, we have produced multiple versions of these devices, which are now in numerous studies. Here's an example of an asthma platform that is being tested out at UNC Health System. This platform has interchangeable boards, so we can have a PPG, photoplasmatogram board, or a potentiostat, or volatile organic compound, or ozone, depending on the specific needs of the use case. So what are the features that enable this kind of response? So first is air quality monitoring. So in this case, we have two sensor technologies. One is a metal oxide sensor technology, and this is by no means a new technology, but our contribution here has been to significantly reduce the power consumption of this technology by building ultra thin metal oxide layers using atomic layer deposition. And these systems, these films can detect ozone down to very low levels, in the case of 20 to 25 ppb, and it can also discern different combinations of gases. We have played around with thickness as a major knob in improving sensitivity, and you can see that very, very thin films, as thin as 4 nanometers, have depicted very high sensitivities to ozone in this case. The other technology that we have is capacitive micromachine ultrasonic transducers. This is a MEMS-based device. You can see that it has, shown here, it has multiple channels. Each channel can be functionalized with different polymers and be used to detect different kinds of VOCs. Again, this device has been tested in mixtures of multiple different VOCs, and it has the ability to discern different kinds of VOCs, such as ethanol, toluene, and xylene. What's interesting about this asthma platform is the ability to get human subject data. And while this work is still going on, I wanted to share with you that we're able to get some surprising and first of its kind reports on healthy individuals being exposed to controlled amounts of ozone exposure, and the result being a reduction in heart rate. So basically, there were changes in lung function noted with a slowed heart rate after low ozone exposure. This suggests that there's an increased parasympathetic tone response detected by slow heart rate. This is, like I said earlier, first report of its kind, indicating that personalized monitoring of ozone and other gases can be very useful in preventing asthma trigger events. The third use case that I'd like to talk about is that of diet management. As you can see on the plot here, diabetes and prediabetes is very prevalent all over the world. Typically, prediabetes is defined when someone's A1C values are between 6 and 6.4. There are many, many individuals that are in this category. And if we were able to provide them direct feedback on their diet and the effect on their glucose levels, we could prevent them from becoming diabetic and hopefully help them become normal. But what's required here is really the ability to detect glucose in a non-invasive manner so that it's comfortable for the user. And our approach here has been to look at sweat. Sweat is an interesting body fluid. It has quite a bit of information, but it also is very susceptible to corrosion or corrupted data, I should say. And it's really important to understand what we're measuring in sweat. But there's also an opportunity to collect sweat in innovative ways. Right now, a lot of the sweat studies that are out there are looking at somebody exercising aggressively to be able to sweat, and that sweat is collected. What we really need is the ability for the person to collect sweat even when they're in their normal environments. And this requires that the sweat collection be non-invasive and comfortable. This is where we have innovation in using osmotic pumps, and I'll talk about that in a minute. So what are the clinical needs? As I mentioned already, we need fluid sampling collection of sweat, but we also need activity and respiration monitoring and ECG. We want to collect biochemical measures such as glucose and lactate, and we want to be able to make correlations between the different sensor data that we're collecting. So for example, in the case of sweat, we are interested in glucose, lactate, but also uric acid. As you'll see in a minute, uric acid is connected to healing of different areas on the skin, including wounds, and having an idea of changes in uric acid are quite interesting. So as I had already mentioned a little bit, sweat is an interesting body fluid. It has a lot of different bioanalytes in them, for example, cortisol and lactate and ethanol. And but current devices that are using sweat require some aggressive exercising, and this makes it difficult to do real-time sensing of common analytes in common settings. So what we are using in our center is the concept of osmotic pressure gradients. Osmotic pressure gradients are the major mechanism that nature uses to move fluids around, such as sweat. And we have pioneered this principle to draw fluid through the skin. This is a patent that is pending, and the idea is that we have hydrogels that are doped with different compositions, and we use those hydrogels to absorb sweat from the skin into this channel that is then connected to a sensor location and then connected to a pad, which I'll share more in a minute. You can see the demonstration down here. These are two different hydrogels doped with different concentrations of dopants. And as these two hydrogels sit together, one hydrogel absorbs the fluid from the other hydrogel, and by day 3, you can see the big change in their shapes. So the hydrogels with higher chemical potential than sweat can enable the extraction of this sweat and enable continuous monitoring. So here are some examples of our sweat collection platform. You can see in the middle graph here that this spot here is where the sweat is collected. It is then moved into this channel, this microfluidic paper channel. Along the way, there are sensors that can detect lactate and glucose, and then the paper pump keeps extracting the liquid out. Continuous sensing is established by printing these electrodes on polyimide film, which is then eventually interfaced to the paper channel. And these are some examples of systems that we have built. And this is, again, just a benchtop demonstration, and wearable platforms are also currently being tested. Continuing on a little bit more with electrochemical sensing, we have also built a flexible biochemical sensing platform that consists of both the optical and the electrochemical patch. The optical patch allows for heart rate and oxygenation, whereas the electrochemical patch allows for lactate and cortisol. Here are examples of some of the results from this multi-analyte electrochemical patch, a biochemical sensing patch, where you can see glucose, lactate, pH, and temperature all being able to get sensed in this patch shown down here. And I had already mentioned that we're also looking at wound monitoring. Here is an example of a smart bandage for integrated wound monitoring. This involves a bioenzymatic system for uric acid detection. It's a wearable system that has the sensors printed on a gauze bandage. You can see multiple and duplicate sensors are placed spatially, so we can get resolution of how uric acid is changing near the wound and away from the wound. This is a mobile platform and allows us to collect the data on an aggregator. It has been tested in clinical studies at University of Miami Health System. So those were some examples of how we are taking use cases and building technologies to meet the requirements of the use cases. But I also want to mention that there are numerous other use cases that require different kinds of sensing modalities, new form factors, and new insights. So there's quite a bit of work that is still a huge opportunity for folks working in this field. We believe that some of our self-powered capabilities can be configured for some of these technologies, but there are still a lot of advances that need to happen in new sensing mechanisms. Here are examples of some new directions that are enabled in this space. For example, you can go inside the body, still provide a battery-free environment by using ultrasound to power those sensors. So whether it's in the aortic valve as a pressure sensor that can be powered by ultrasound, or whether it's a stem cell patch on the heart that is also powered by ultrasound. You can also have injectable biometric sensors. This particular device has photoplasmatogram, accelerometry, thermometry, and wireless data transfer. And this is work that we're doing in the center with our research team headed by Albert Boskert. There are some other directions, even with environmental sensing. You can have environmental sensing that face inward and look at the breath, or even the skin vapor coming out to be able to detect body conditions like metabolic states or even COVID-19. And so there's a huge opportunity in looking at breath and skin vapor as a sensor for understanding what's happening to the human body. So in the last few minutes left here, I'd like to also share with you that in our center, we have quite a bit of entrepreneurship going on. There are numerous technologies that we're generating, and we have been able to create quite a few startups. For example, our textiles work with the smart textiles integration and electrode integration has produced a startup called Next Systems. Our micro machine membranes is being applied towards different applications in ClearSense. Our low power electronics is a very huge success right now, ever active. Microneedles that I didn't talk about much today, but they are also very critical in getting interstitial fluid that has even a more accurate content of glucose has led to DermaSense. Our spirometry for asthma management is Vital Flow. We also have just sweat sensors for hydration. This is licensed by a company, On Division. And our ozone metal oxide sensors technology is Olftec. So these are all startup companies that are currently active and benefiting from the technology development in the center. So finally, I'd like to summarize with looking at future opportunities. Some of you in the audience may be working in this area or perhaps are thinking about working in this area. And I think there are quite a few things that are huge gaps. For example, we need new modes of energy harvesting that take us beyond a milliwatt of power. If you can go beyond a milliwatt of power, you can enable quite a few different sensing modalities. You also need new sensors. It's great that we have ECG and PPG, but we need sensors for example, core body temperature or blood pressure measurements that are accurate. And so some new advances here are necessary. I didn't talk about data. However, artificial intelligence and machine learning is critical. And applying these techniques on multiple data streams is very important and a huge opportunity. Another area is reconfigurable sensor systems, where the same sensor system can be reprogrammed based on the context and either change the sampling rate of a particular sensor or completely change the sensing target. So this is an area that could be very interesting. And there are so many use cases. Of course, we have COVID, but even opioid, pain management, sepsis, dementia, seizures, and more are all areas where significant advantages can be can happen with the technologies that we are building. So I'd like to conclude now and thank first of all, the funding agency of National Science Foundation that has funded all of our group here. You can see all the PIs and their students that have contributed to this work. I'd like to also thank all of the assist universities, the industry members, and all of the individuals involved. So with that, I really thank you for your time. And as I understand it, I will hopefully get questions from you that I'll be able to happily answer by email. Thanks very much.